So as we discussed in this lecture, we'll now consider filters or operators or kernels that are of size more than 1 cross 1. So we'll consider filters that are of size n cross n. So they operate on more than one pixel at a time, typically on an n cross n neighborhood of a pixel. So we can define the neighborhood of a pixel located at I comma j as nij, and this neighborhood is of dimension n cross n, where the most common values for most of the common filters, the value of n is usually 3, 5, 7 or 9. It is usually unlikely for a filter to be of size more than 11, and the filter size is more than 17. For example, if n is greater than 17, then the process would be computationally very expensive, and in this case it is advisable to perhaps take the computation in the frequency domain rather than operating in a spatial domain. But usually most of the filters that we'll be considering, they would be of size 3, 5, 7 or perhaps 9, not more than that typically. So we'll be discussing filters of size n cross n, where n is the size of filter. They take the neighborhood of a pixel into account, so they operate on a pixel I comma j by taking the small neighborhood of pixel into account, denoted by nij, where nij is n cross n. And these filters are centered on a pixel on which they are operating, and that's why we select the value of n to be odd, because if we select an even value, then it would not be possible to center the filter on the pixel location I comma j. But the filter is odd, then we can center the filter on the pixel location I comma j. For example, assume that we have this image and we want to apply an operator of 3 cross 3 on this pixel over here, then the filter would be centered on this pixel and take 3 cross 3 neighborhood of pixel into account. So to take this neighborhood, 3 cross 3 neighborhood, centered at I comma j, ith row and jth column, and we'll take all these pixels in the neighborhood into account. We'll operate on this neighborhood and will give us the resultant value so we have 1, 2, 3, 4, 5 divisions. 1, 2, 3, 4 and 5. Likewise we have 1, 2, 3, 4 and 5. 1, 2, 3, 4 and 5. So to compute the transform value of this pixel, to take this neighbor into account, operate on this neighborhood and give us the value for this pixel in the transformed image, which is obtained by applying this filter on each of the pixel I comma j in the input image. So on this pixel, so we'll see we typically add additional rows and columns in an image when we operate on corner or boundary pixels, and we extend the boundary by n rows and n columns. So when it operates on this pixel, to take this extended image into account, and usually we just append the image with zeros, or sometimes we append it with ones, or sometimes we just append these additional rows and columns by copying the top row or leftmost column, and likewise here top row and rightmost column of an image. Likewise, when we are here, we can append the bottommost row, bottommost row and either of these columns, depending on whether we are on the left side or the right side. So it operates over here and gives the value for this pixel. It operates over here, gives the value of this pixel, operates over here and gives the value of this pixel. Again, taking all these neighborhoods into account. So just like we discussed in the histogram equation, where the histogram equation, the operator operates iteratively on each of the pixels in an image, but the dimension, the operation region was just 1 cross 1. Here we have an operation region n cross n. So the pixel takes the central pixel value as well as its neighbor into account and runs some transformation depending on what function it is using, and gives us the transformed pixel value in the transformed image. So to summarize this, our filter is n cross n, where n is odd, usually 3 or 5 or 7 or 9, most common values. It operates on each of the pixels via some operation on location I, j, taking the neighborhood of the pixel into account. So we have not indexed this operator with I, j to denote the spatial independence, that is, the transformation function or the filter doesn't change based on the location where we are applying this transformation. So as we had discussed earlier as well, earlier in the previous lectures, we are going to discuss the spatially independent filters that do not depend on the spatial location. And also we are going to discuss filters that do not depend on the value of the image. So the transformed value definitely depends on the value of the image and its neighborhood of pixel I, j. But the filter, the filter and the kind of operation it is applying, it doesn't depend on the value of the pixels. So these are the two assumptions that we discussed earlier as well, that we are going to discuss pixels that or filters that are spatially independent. So we are going to use spatial independence. That is a transformation or function, or the transformer or the operator doesn't depend at what location it is being applied at, and also it doesn't have any correlation. The kind of operation it is performing and the components of a filter do not depend on the value of the pixel or its neighborhood. For brevity, we'll just drop this notation of neighborhood. When we discuss a filter of size n cross n, we will implicitly assume that it operates on a pixel I, j, considering the n cross n neighborhood around the pixel. So we'll just drop this notation of nij every time for the purpose of brevity and for the purpose of clear notation, so that we don't just overcomplicate as to what we are writing over here. So now we'll start our discussion with some of the filters that are useful for image smoothing, and we'll see most of these filters are linear. So we'll start our discussion with linear filters. That is, they are linear in the pixels and the neighborhood of a pixel. What it means is that the operation that would be performed on the neighborhood of pixel I comma j would be a linear operation in the image pixel neighborhood. So we'll begin our discussion with some of the linear filters. And one of the most common operations in not just in image processing, computer vision, but also in deep learning is a convolution or correlation operation. So these are the two most common operations that filter performs in the neighborhood of pixel I comma j to get the value of the transformed pixel. So that's why you would have heard the term convolutional neural networks. It means that the operation that is being performed is a convolutional operation, and we'll see what is convolution and what is correlation in 2D images. So next we'll briefly consider both the convolution and the correlation, and we'll give the subtle difference between the convolution and correlation as well.